Here we're going to return to an older concept that we talked about when we talked about two-dimensional motion, when we were in kinematics. We talked about this idea of center of mass. And the center of mass is very, very important for conservation of momentum, because when we look at a system, it's the center of mass where momentum is conserved. Basically, we can look at a system of particles as having both internal and external forces. The external forces being forces that are going to act on all the particles coming from the outside. And that's what's going to change the way the center of mass moves. The internal forces have no effect on the center of mass. So taking a look at our center of mass, and again, returning back to our concept of kinematics and projectile motion, we said for a person, it's not so much any part of their body which is necessarily going to follow a parabolic trajectory. We said that there's a center of mass, a place where the average mass is concentrated, which is going to follow this parabolic path. So when we watch how an athlete moves in the long jump, in the high jump, in the hurdles, we follow the center of mass and watch that undergo this projectile motion. So how do we come up with the center of mass? How do we locate the center of mass? Well, if we have a uniform body, what we need to do is add up all the little parts of the body itself and look at what their individual mass is and how far they are from some reference point. In this case, we would use the origin right here. And if we add up all of their positions multiplied by their masses, we would get, on average, a position which would be located at the center of mass. So again, if we're looking at a more complicated system and we want to see how it behaves, we would want to follow the center of the mass of the system. Very good example of this, in fact, would be fireworks. When fireworks are launched, you basically have a shell that's intact. But if there is no force of friction, as the firework exploded, all the individual pieces would go off in their own direction, but the center of mass of the entire system would remain in a parabolic trajectory. Of course, the force due to friction has a larger effect on the individual particles. So this actually causes them to reach terminal velocity pretty quickly after the firework goes off. Okay, so again, we're going to calculate the center of mass. Again, this is going to be important for watching how a system evolves, especially, as we conserve momentum, as we conserve kinetic energy. Let's start out with a system of individual masses, okay? Let's say that we have these 5 masses right here, and we want to know where the center of mass is. Well, the center of mass is located at the sum of the position vectors times the mass of each particle, okay, divided by the overall mass of the entire system. So the way that I would do this is I would calculate each one of these vectors. Now remember, these vectors here are 2-dimensional. If we have 3-dimensional vectors, we'd have to do the position in the x direction, the position in the y direction, the position in the z direction. We would multiply that by their individual masses and then divide by the overall mass of the system. In this case, the center of mass is located here. Even though there are no particles located there, that would be the center of mass for this particular system. Now, for a continuous body, we have to use a bit of calculus for this. In this case, we have a body which is, we're going to assume is uniform. Probably shouldn't have used this bevel right here because that means that it's not going to be uniform in the x and y direction. But let's say that it's uniform. If we take an infinitesimal volume of mass right here, we'll call this little mass dm, and we want to locate where the center of mass for the system is, what we have to do is something similar to what we did before. Remember, in calculus, the summation is really analogous. I should say that the integral is really taking the summation where you take the individual particles to an infinitesimally small scale and essentially add them up. So again, this integral is really a summation of infinitesimal parts. So we integrate over the position vector times this infinitesimal mass, and then divide by the total mass of the system, which in this case, we integrate over the entire structure right here. So looking at this, let's take a look at a simple system, first of all, where we have discrete masses, and then we're going to look at a continuous mass, which is a little more complex. Again, take the orthogonal components and separate them. So instead of, looking at this as just the position of the center of mass, we want the X and Y coordinates of the center of mass, okay? So here we change our summation to the summation of the mass times the position in the X direction, or the summation of the mass times the position in the Y direction. And pretty straightforward here. So M1 times -2 meters, M2 times 0, M3, which is 4 times 1. That would give me the summation of this numerator, this numerator in the X direction. And then the total masses, 5 plus 5 plus 4 is 14. And that would give me my X position. Do the same thing for the Y direction. Here's my X position right here. So I see that my center of mass is a little bit to the left of the Y axis at -0.43. All masses are either on the X-axis or above the X-axis, so I don't get a positive Y component. In fact, the only non-zero contributor is this one right here, and I get 0.71 meters above there. So center of mass is pretty simple for discrete bodies. Obviously, the more bodies that you have, the more terms you'll have in the summation, but the technique is no different. For a continuous shape, it's a little more tricky, okay? For a continuous shape, and I've chosen, they don't look like easy functions, they actually are easy functions. I've chosen two functions here that create the upper and the lower bound for the system. Now, this is a more common problem that you run into in Calc 2 or in Calc 3. So some of you may not have come to this yet. But basically, I'm going to put the upper bound as being equal to the square root of 1/3 of X, and the lower bound is going to be 1/9 X squared. So, of course, you know that when we have our X squared, we get a parabola. When we have the square root of X, it's actually parabolic in the Y direction. That gives me this neat shape that's fairly easy to integrate. Say fairly easy to integrate. But again, I'm going to integrate the X position, as a function of mass, and the Y position as a function of mass, and divide it by the total mass of this system. Now we're going to assume that this is uniform. If the density is not, uniform, it's not isotropic, it creates a more complicated function than what we have here. But here I've kept it pretty simple with a constant density. So again, the total mass, I'll do the total mass first, is equal to the integral of all the mass of the system. That's basically the density times the total area. The total area of the system is the area bounded by this upper bound minus the area bounded below this lower one. So that gives me this function minus this function integrated. I forgot the dx. There should be a little dx sitting out here for this. And I do the integral of x to the 1/2 power, which gives me 2/3 x to the 3/2 power. The integral of x to the 2nd power gives me x to the 3rd divided by 3. And as I put in my limits here, you see what I get. And this is easy. This is why I chose this really simple integral. It's actually just 2 minus 1, where the mass is equal to the density times 1, whatever the units I'm using, it'd be 1 meter squared or centimeter squared. whatever I'm doing right there. So that's fairly straightforward. I'm not really worried about this, even though the dimensions of mass and density are different. Again, I'm assuming that it's density times, the volume right here, but it's going to cancel out anyway, so I don't have to be that careful. So now I'll do the same for X and Y. Okay, here's where it gets a little more tricky when I get to Y. So I integrate with X dm. So now I'm going to have this extra term that I didn't have before. So instead of having X to the 1/2 times some constant, I have X to the 3/2. Instead of having X to the second, I have X to the third. And of course, I integrate that and I see that I get a little more complicated. Okay, so I get 27 over 20 times the density. Now, you'll see that I call this the moment in the Y direction. That'll be important later on when we get to this in rotational motion. So I'm just trying to be consistent here. But again, this is a fairly straightforward integral to do. When I do the integral in the Y direction, I'm going to have to flip my functions around to be dependent on Y instead of X. So, really, the lower function now becomes Y squared. The upper function becomes the square root of Y. And you can see that if you just rotate, invert the whole thing right here, that this function increases by Y squared, this function increases by the square root of Y. And now we're going to integrate in the Y direction instead. So basically nearly the same, integral that I had before, just different coefficients. And I get 9/20 rho. Okay, so once again, we need to find what the center of mass is in the X direction, the center of mass is in the Y direction. I take my previous result divided by the mass, okay? When I integrate in the X direction, it was 27 over 20 times rho. The entire integration of the mass was rho, and again, we're assuming that rho is times a unit of volume. Rho divided by rho cancels out, so that's why I wasn't really careful with that. I get 27/20, and that's my X position. And yeah, that looks like 1.35. That's pretty much what I would imagine the center is right there. Same thing for the Y direction. I get a slightly different number, 0.45. But if we look in the Y direction, yes, in fact, it goes up only 1 unit in the Y direction and 3 in the X direction. So, this is actually a little bit skewed. If I really plotted this with both axes evenly, it'd probably go up at an angle like this. And if you use the argument of symmetry right here, you draw a line right down the center of this, an axis, our center of mass would go through that too. So that's how you calculate the center of mass for both discrete and continuous shapes. Now, here's something that's important. For a system, there are always internal forces and there are external forces. Let's say that these are charged particles. So maybe they have an attractive and a repulsive force, depending on their size. Let's say that this particle right here is attracted to both of these particles, but both of these particles repel one another. It doesn't matter what's going on right here. But we say all those forces are internal. Really, what happens here is because these are force pairs, they all cancel out with one another. Like this force cancels out with this force, they're equal and opposite by Newton's third law. This force cancels out with this force, they're equal and opposite by Newton's third law. This force cancels out with this force, they're equal and opposite. So in this case, the internal forces will do nothing to the overall center of mass for the system, okay? These particles will eventually come together right here. This particle will go off in this direction right here. Oh, I guess that this force is going here. This particle will go off in this direction. These two particles will come together. But the center of mass will remain the same as they're moving through space. If these particles are also under the force of gravity, we would say the force of gravity is an external force. So now all particles would feel this external force pulling them down. But an external force does affect the center of mass. and we can use our form of Newton's second law for the change in mass as a function of time. So internal forces don't affect the center of mass, but gravity, for instance, would affect the center of mass. So let's say that these were particles that were, launched, in a parabolic trajectory. The center of mass would follow a parabolic trajectory while the particles would move within the system right here. And again, we can see that it's a center of mass that really is going to follow this constant acceleration, even if the individual particles have a more complex acceleration going on. Because remember, these particles are experiencing internal forces and external forces, but the center of mass doesn't feel the internal forces. It's just going to follow whatever is affecting it. Here's an interesting photograph, and I lost the attribution for this, so I'll try to find that. But you can see here's a two-particle system, and if we trace out the center of mass for the system, it would follow a nice parabola just like this. Hopefully I got that correct. But notice the rider comes off the bike, and although there is a brief internal force, the rider is pushing themselves off the bike. I hope they landed on something soft, because that's quite a distance to fall. So it's like a ski slope type thing. So they probably slid down it. But in any case, notice how the bike and the rider undergo their own parabolic motion after they separate, but the center of mass stays the same. Now, center of mass is important for planetary orbits. And if we look at our own solar system, the sun does actually orbit what's called a barycenter. It orbits something that is constantly changing because we have 8 fairly massive bodies that are constantly pulling on it. We think of the planets as going around the sun. They actually go around the center of mass of the solar system. That's also true for the Earth and the Moon. The Earth actually is in orbit of the center of mass of the Earth-Moon system. But the Earth is so much more massive than the Moon that this barycenter actually exists within the diameter of the Earth. So let's do that calculation. The mass of the Earth is 5.97 times 10 to the 24 kilograms. The Moon is much lighter. Okay, it's about a magnitude of 2 lighter than the Earth, or less massive. Now, the average distance between the two, the radius of orbit of the Moon, is 3.82 times 10 to the 8 meters. That does vary a little bit because it's an elliptical orbit, but this is pretty constant. So where's the average center of mass for the system, with respect to the Earth? Okay, so we look at this, and we're going to use a coordinate system in the Earth's frame of reference, where Earth is located at the center of this coordinate system. We say that in this case, we won't do X and Y, we'll do radius, because it's constantly evolving. We don't want to complicate the system. But I say that the radius, or the distance of the center of mass from the center of the Earth, because that's our center of our coordinate system, is the radius of the Earth from that system, which is 0, times the mass of the Earth plus the radius of the Moon's orbit times the mass of the Moon. So our first term is going to be 0. We just have the radius of the Moon's orbit times the mass of the Moon divided by the total mass of the system. And we get that the radius of the or the distance of the center of mass from the center of the Earth is 4.65 times 10 to the 6 meters. Okay. Now, this again is within the radius of the Earth, because the Earth has a radius of 6.37 times 10 to the 6 meters. But it's pretty much in the mantle of the Earth, where the Earth is actually wobbling around the center of mass once every month, the moon goes around the Earth, and it's approximately, and the Earth goes around its center of mass. So in this case, we have an internal force, and the internal force is a force of gravity between the Earth and the moon. The external force is the force of gravity from the sun and the other planets. So as we go around the sun, we sort of wobble a little bit in our orbit, and it's not a perfect ellipse. There are some perturbations from the other planets, and there's also the perturbation from our own moon.